Hey MSA. So this is a recording of the ions, isotopes, and radiation presentation. As big as I can here. So what is an isotope? An isotope is a variation of an atom that has more or less neutrons than is common for that atom. Really, you can call an isotope like the common version of that atom too, but generally when we're talking about isotopes, it's because we're talking about the variations that have more or less neutrons than they normally would. So how do we know what's common for an atom? Well, we can look to the periodic table. This is the periodic table. You can tell that it is the same in all languages. It's set up in this organizational way where it's organized by how many protons each atom has, because the number of protons makes the thing what it is. And then there's actually patterns, like a lot of different patterns about how things interact with each other from one side of the table to the other. You can see that it has the atomic mass of each atom, which tells you how many neutrons it has, as well as the protons, which are the atomic number. There's a symbol there that shows which element it is, and those symbols are the same across languages. So how to read the periodic table: we have the atomic number, which is the number of protons right there. We have the atomic mass, which is going to be right here, which is the number of protons plus neutrons, since each of those has an atomic mass of 1. The atomic name is going to be carbon, and the atomic symbol is that C. And like I said, that is the same in all languages, actually, for all atoms. So the atomic number determines what the atom is. So carbon is carbon because it has 6 protons, and that does not change. The atomic mass, so for example, like if it was to lose a proton in the course of radiation or whatever, it would become something different. It would become a different atom. The atomic mass is the number of protons plus neutrons. So a small but consistent percentage of atoms have a different atomic mass. And the way that I like to think about that and remember that is that a small but consistent percentage of people and animals have genetic differences. For example, albinism, which means that you lack the melanin that you would normally have. So you can have these pasty white kids with brown families, and you can have these pasty white alligators with, from a regular alligator family. Just like that, atoms can have different numbers of neutrons in rare cases. So one example of this that we use for a lot of things is carbon. Carbon usually has 6 protons and 6 neutrons, like most of the time. But sometimes it will have an extra neutron, and sometimes it will have 2 extra neutrons. And to find it, so let's look at like the percentage of each one. So 98.89% of carbon is carbon-12. 1.11%, which is not nothing, right? That's like 1 in 100, so there'd be like 20 kids in our school. If we were a school of carbon, about 20 or 30 kids in our school would be carbon-13. And then maybe 1 kid in our school would be carbon-14, something like that. I mean, like, that's just kind of like thinking about proportionality and percentage-wise. So yeah, 0.100% of all carbon, which there's a lot of carbon in the world, lots of things are made out of carbon, is carbon-14. So this big question is, why do we care about isotopes? Why does it matter how many neutrons a carbon atom has? Well, the answer number 1 is that we can use it to do radiometric dating of archaeological materials. So I'm going to let you watch this video on your own. I guess I'll kind of tell you, I'll let you watch it real quick. Here's some main points here.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of 2 different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, Sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
Okay, thanks, Michael. So, to recap what he was saying there, so living things continuously replace their atoms when they live, but stop when they die. You guys may have heard that we are like entirely new beings after 7 years. All of our cells and molecules have been replaced every 7 years. It doesn't happen like all at once, obviously. We're continually renewing our cells, and some parts renew faster than others. But within 7 years, even like the bones in our body are like completely different cells than they were before. They've been remade. So the ratio of carbon-14 is going to be the same as the natural ratio as long as they live, but it's going to start dropping as soon as they die, because they're not renewing the carbon in their bodies anymore. So that percentage, that 0.01 percentage of carbon that's in their bodies is going to start dropping. It's going to start emitting radiation. It's going to cause to be different. So, so the most widely known form of radiometric dating is carbon-14 dating, which works for like most human civilization. It works up to like 60,000 years ago, and most of like recorded history that we know about from written things is like within the past 4,000 years. I think the oldest humans that we know about are, I mean, there's a couple that are like, some of the oldest human fossils are like a couple million years old, but for the most part, many of the archaeological things that we're looking at can be carbon dated. But carbon-14 dating doesn't work on dinosaur bones. The half-life of carbon-14 is only 5,730 years, so carbon-14 dating is only effective on samples that are less than 60,000 years old, because that's like, once you get down to like, 10 half-lives, you're basically at like pretty much nothing at that point. So dinosaur bones are millions of years old, like 60 million years or so to like 200 and something million years old. Some fossils are billions of years old. We have this trilobite that's probably like, I don't know, could be like 1 billion years old. Some of the oldest rocks on the planet are like 4 to 5 billion years old. So to determine the ages of these specimens, scientists need an isotope with a very long half-life. So some of the isotopes used for this purpose are uranium-238, uranium-235, and potassium-40, each of which has a half-life of more than 1 million years. So unfortunately, there's a complication because those elements don't exist in dinosaur fossils. We don't have uranium inside of us or potassium-40 in us generally. So scientists, what they do is they look at the geologic, like the rocks, the stratification of the rocks, and they're looking for layers. So they need a layer of igneous rock, meaning like lava dust, basically, like where there's been a volcano and that dust has settled, or where there's been, lava moving through that area, because igneous rock, like radioactive materials, those giant atoms can be created in the super crazy processes inside the earth. So magma will contain those things, like volcano magma will contain those things. But dinosaurs get fossilized in the sediment of rivers. So like those uranium and things are just not going to show up in the fossils themselves. So what scientists do is they look for like bookends of igneous rock so that they can test the ages of those, and then they can find out, the age of the dinosaur fossils that are between those rocks, between those ages. They're like bookends. They give a beginning and an end to the period of time when the sedimentary rock formed. This is igneous rock. It's kind of sharp, kind of shiny, kind of cool. So another reason why we care about isotopes is because of hydrogen isotopes, which give us nuclear reactions and heavy water. So this is a hydrogen atom, just a simple electron and proton. Here are some isotopes of hydrogen. Hydrogen usually does not even have any neutrons, but sometimes it'll acquire one, and that is called deuterium because it has deux means two, de if you are speaking French, de, trois. Protium, deuterium, 2 atomic mass, and tritium, which has 3 atomic mass because it has 2 neutrons in there. And these 3 are the most stable isotopes of hydrogen. They have made other ones, but like it's just crazy. Like that would never happen. And they don't hang around for very long. So the abundance of these things. 99.98% of hydrogen is what we think of as hydrogen. 1 proton, 1 electron. Hydrogen is like so prevalent in everything. I mean, it is part of most atoms, and most of it is stable. But 0.02% of hydrogen has a neutron in there. And then not even worth saying the number, a trace amount of hydrogen has 2 neutrons in there. And when it does, the half-life of that hydrogen is 12.32 years. So like within 12.32 years, half of that hydrogen that has 2 neutrons is going to spontaneously radioactively decay, meaning it's going to lose a neutron. So another cool thing about hydrogen isotopes is that they are the way we can create nuclear fusion here on Earth. Nuclear fusion and nuclear fission are the two main, those are the sources of like a ton of nuclear energy when we're talking about nuclear sustainable nuclear energy, or when we're talking about the energy created by nuclear bombs. It comes from nuclear fission and nuclear fusion. So this is also how light and heat is created by the sun. So if you take a deuterium atom and you take a tritium atom, which are both hydrogen isotopes, you smash them together, they fuse, produce a ton of energy, and you get a helium atom, and you get a neutron that flies off. And neutrons are crazy. They have a lot of, they're super radioactive. They can go through like anything. This is a very, very powerful thing that happens here. And this is, we've been able to produce this on Earth. So deuterium is also produced for industrial, scientific, and military purposes, starting with ordinary water, a small fraction of which is naturally occurring heavy water, meaning it's made of deuterium. And then separating out the heavy water by the Girder sulfide process, distillation, or electrolysis. It's also used as a moderator in nuclear reactors, so it absorbs some of the energy. It can pick up or lose its neutrons to kind of protect the giant explosions that are going on inside nuclear reactors. Tritium has to be made. I mean, there's a trace amount of it, but such a small trace amount, they didn't even put the number there. It is made in production nuclear reactors designed to optimize the generation of tritium and special nuclear materials such as plutonium-239, which is a radioactive chemical. It is produced by neutron absorption of a lithium-6 atom. So, okay, so we've seen this before. This is the nuclear stability patterns of radioactive decay. This black line here is where the atoms are naturally stable, as far as the protons and the neutrons are going to be about the same. And then we have where they're not stable. You can see these different kinds of radioactive decay that we have. I have such a short amount of time left, and there's so many things I want to tell you about still. Ions are where it's lost or gained electrons, which is normal, right? Things are always losing and gaining electrons. But when an atom tends to have a negative or tends to have a positive charge, that's called an ion. And what that does is it creates these really great polar molecules, like table salt is one of them, which is a positively charged sodium atom plus a negatively charged chlorine atom, and they clump together in these really solid ways. You can also see that water molecules have a charge also. I'm about to be cut off. Hold on a second. Anyways, take a look at these cool last few slides. Very, very cool stuff going on here. Read them for yourself. Okay.